In this video, we'll learn to think of the absolute value as a distance, and then we'll use this together with a lot of other methods to solve equations and inequations involving absolute value. So first, we say that we can interpret the absolute value of x as the distance of x from the origin. And indeed, just think, for example, of 3 and -3. They are both 3 units away from the origin, and indeed, their absolute value is 3 for both of them. So the absolute value in that case, indeed, is the distance from the origin. And this will hold for any number, so that will be the distance from the origin. Now let's look at the picture we have below. I'm looking at that. If we want to calculate the distance between x and a, so that is this distance here, what we would normally do is do the large one minus the small one. That's your x minus a. And this turns out to be the same as the absolute value of x minus a. You may just want to try a few values. If, for example, you want to know how far apart 3 and 7 are, what you would normally do is do 7 minus 3 and you get a 4, that's your distance. But now if you subtract it in the other order and you did 3 minus 7 instead, you would get minus 4. But please note that once you put the absolute value around, you do get the distance. So basically, what this is telling you is if you want to find a distance between c and x, what you could just do is subtract them in any order and then take the absolute value. You may be wondering why we need that. Why don't we just subtract the large one minus the small one? Well, it turns out that if one of your two numbers is x, you don't know its value. So for example, if you look at this example where you have x minus 7, and if you want the distance between x and 7, given that you don't know which one is larger, what you will do is subtract in any order, so x minus 7 for instance, and then take the absolute value, which will guarantee that what you get is actually the distance between them. We will also use this backwards. Whenever we see something which looks like absolute value of x minus c, we know that we can think of it as the distance between x and c. Let's see how to use this by solving an example. So we know that the absolute value of x minus 7 is 5. We just rewrite this thinking of distance. That really means that the distance between x and 7 is 5. We can now easily represent this on the number line. So 7 is here, and then 5 units away from 7 we have 2 points. So now 5 units away, move 5 units. We have these 2 points. This one is 12 and this one is 2. So the solutions are 2 and 12. So we use this method because the question really says interpret the absolute value as a distance. Of course, for a question like that, another thing we could have done, that would have been method number 2, we could have said that if the absolute value of a number is 5, then the number must be either 5 or -5. And then we managed to get rid of the absolute value by doing this. And this equation tells you x is 2, and this one tells you x is 12. So 2 different methods to solve this. So let's go back to equations, and let's see how we could solve the following equation. Let's try to think of several methods. What you could do is pause the video and try to figure out as many methods as you can. So the first method we could use would be to just use the definition. What we would do with this is just to say, well, let me treat 3x minus 2 as one number. So what it says here is that the absolute value of this number I'm looking at is equal to 7. And that can only happen if either my number is itself equal to 7 or my number is equal to -7. And then we keep solving, and that gives us one method. Can you think of another one? Probably what the idea that came to you since we just did it was to think of the absolute value as measuring a distance. Absolute value of 3x minus 2 is equal to 7 seems to tell you that the distance between 3x and 2 is 7, which is not very useful. So what you can first do is actually rewrite your equation. Then we know that since here we have a product, we can split the absolute value, which is what we will do. And so we can rewrite this 3 times absolute value of x minus 2/3 is equal to 7. And dividing both sides by 3, we get the absolute value of x minus 2/3 is 7/3. And now we can solve. The distance between x and 2/3 is going to be 7/3. So that will give us 1 point here, which is going to be 9/3, so really 3. And on the other side, we subtract 7/3, so 2 minus 7/3, and that's going to be minus 5/3. That gives us our other solution. We're trying to come up with as many solutions as possible, so let's try to find something else. Did you think of something? One thing we could do is try to sketch the graph of this absolute value. So we could graph y is equal to absolute value of 3x minus 2. I'm just trying to give the idea here, so I'm not going to write the details. So you would get something like this, and then you would want to know when it's equal to 7. So let's say 7 is somewhere here. And that would give you 2 values. Your solution would be the 2 points here on the x-axis, right? Here and there. And we said we could think of 4 things, so let's try to keep looking for an idea. We could also do cases. And that means we would like to split the domain just to make sure that on each part of the domain we don't have an absolute value anymore. The way we do this, we really wonder how to get rid of the absolute value, and that's when you know what the sign of the thing that's inside it. So the 2 cases you would have is either 3x minus 2 is greater than or equal to 0, and in that case you would be able to rewrite your equation without the absolute value, because the absolute value of a number which is greater than or equal to 0 is the number itself, and you get a nice equation without an absolute value. Case 2, what happens if what's inside the absolute value is negative? Well, in that case, the absolute value of a negative number is obtained by multiplying the negative number by -1. And again, you get an equation without an absolute value. We'll talk about this later. Usually we tend to use the first 2 methods for easy examples, just like an absolute value is equal to a number, because these are much easier. Now when it gets hard, sometimes you have to use the more complicated method. So in short, method 1 and 2 are simple, but they work only for simple equation, and method 3 and 4 are a little harder to implement, but they will help you solve even difficult equations. This is just a summary in form of a toolbox of the tools you have to solve equations that involve absolute value. You could use the definition, saying that if you know that the absolute value of something is, let's say, 3, well, there are only 2 numbers whose absolute value is 3. So that way you get rid of the absolute value, and you can isolate x and finish solving. You could also split the domain. So if you split the domain, you will have cases, and on each part of the domain you will be able to rewrite your equation without absolute value. You could also use the interpretation of the absolute value as a distance. So if you see something which looks like absolute value of x minus 2, you know that this is the distance between x and 2. And finally, you could sketch a graph. We will do an example of this later on. So it's a good idea to keep all those possibilities in mind. So let's look at an example and see what we can do. So we have this equation. It's an equation because it's an equal sign which we want to solve. And we can see that in that case, just the definition of the absolute value won't help very much, because the absolute value is equal to something, but something which varies. So it's very easy to know which number have an absolute value equal to 4 or to any fixed value, but not that. So this really wouldn't work. Same thing for the distance. So we're left with our two other methods. So the first one tells us that we could use a graph or graphs to be able to solve. So do you see how we could do this? We first want to solve this equation graphically. What we could do is sketch the graph of y is equal to absolute value of x plus 2, and sketch on the same diagram the graph of y equal negative 2x plus 1. So we want these two y's to be equal, and the two x's will be equal too. So that means that we're looking for a point that will be both on the first graph and on the second one. That means we're really only looking for the point of intersection. Now the good news is that this is just an absolute value, so just shift it from y equal to absolute value of x. And this is the equation of a straight line, so it shouldn't be too bad to draw those two. The second method we wanted to explore was to split the domain in order to rewrite the absolute value in an easier way. So, the absolute value of x plus 2 will sometimes be equal to x plus 2, and that's exactly when what is inside the absolute value is greater than or equal to 0. With this in mind, we can design our cases. Our case number 1 will be, so really we can see that this means x is greater than or equal to negative 2. Case 1, x is greater than or equal to negative 2, which in turn means x plus 2 is greater than or equal to 0. And for these values of x, we can say that absolute value of x plus 2 is x plus 2. And we get a nice equation, because now the way to rewrite the original equation is this, which we can easily solve. Our second case will correspond to the case when whatever is inside the absolute value is negative, because again, when that's the case, we know what to do. So case number 2, it's when x plus 2 is negative, so really when x is less than negative 2. And in that case, the absolute value of x plus 2, being the absolute value of a negative number, it's just obtained by putting a negative sign in front of that. Again, we sub this in the original equation, and we're left with an equation which doesn't have an absolute value. Let's do it. Let's first sketch the graph of y is equal to absolute value of x plus 2. Well, we know exactly what this one looks like, because we get it by shifting the graph of y equal to absolute value of x, and then now we need to think. We added something to x, so we're moving horizontally, and we're moving it 2 units to the left. Again, we can see this because whatever was happening at 0 now happens at negative 2. Let's sketch this one first. So we can calculate a few values. So well, we know that here we get negative 2. When x is 0, we get 2. So we know what kind of shape we're getting, right? We're getting this V shape. And then it's symmetric. So when x is negative 4, we get 2 again, somewhere here. So what we represented here in blue is the graph of y is equal to absolute value of x plus 2. We even know the equation of each of the branches. This is really x plus 2, and here it's really the opposite, minus x plus 2, because that corresponds to the cases when what's inside the absolute value is negative. Now let's sketch the graph of y is equal to negative 2x plus 1 on the same drawing. We know that this is the graph of a straight line, and we pick a few values. When x is 0, y is 1, that gives us this point. When x is negative 1, we get 3. So 3 is here, so that gives us that point. And with this 2, we can actually sketch the graph. So this is y is equal to negative 2x plus 1. As we said, solving this equation there really means that we're trying to find the points of intersection. Well, there is only one and it's there. So we need to find its x-coordinate. From the drawing, it's pretty clear that it's something between negative 1 and 0, but we would actually like to find the exact value. Let's do that. So we can see that it's the intersection of this branch and this branch as an equation equal to y is equal to x plus 2, and then this straight line. So what we need to solve is, when is x plus 2 equal to negative x plus 1? Let's add 2x to both sides. We get 3x and subtract negative 2. 3x is equal to negative 1, so x is equal to negative 1/3. And we're pretty happy with this result, because it's really, I mean, the diagram is not totally precise, but really negative 1/3 seems something like very consistent with what we were expecting. So let's sketch these two graphs and find the points of intersection. Let's do y is equal to absolute value of x plus 2 first. This one is obtained from the graph of y equal absolute value of x by just shifting to the left. So let's place this on a number plane. So when x is negative 2, so we can add values here. When x is negative 2, the absolute value is 0, so we get this. When x is 0, we get 2. So that's 2, that's negative 2. And so we get this portion of the graph, and its equation is y equal absolute value of x plus 2. Now let's say so we get 2. When x is negative 4, for example, we get absolute value of negative 2, which is 2 again. So for negative 4, we get 2 again, and it's this value. And that's the other part, and the equation of this one is minus x plus 2, because we know that this time we're taking the absolute value of a negative number, and this is obtained by putting a negative sign in front of it. Let's move on to the other graph. So our other graph is y is equal to minus 2x plus 1. That's the equation of a straight line. So again, we only need 2 points. When x is 0, we get our y-intercept, which is 1. So I go through this point. And when x is, let's say, negative 1, when x is negative 1, we're going to get 3. When x is negative 1, we get 1, 2, 3. It's here. And this is y equal to negative 2x plus 1. Our goal was really to solve this equation up there, which really corresponds to the points of intersection of the graph. The reason for that is this is the y-coordinate on a point which is on this graph, and that is the y-coordinate of a point on this graph. So if 2 points have the same x and the same y, then they're the same point. So what we are after is really this value. So we can see from the diagram that it's probably going to be a number between negative 1 and 0. Let's check by doing our calculation. So if our point here, our red point is on both, it means its y-coordinate is equal to x plus 2, which we get because we know that it's on this part of the graph. And the equation of this part of the graph is y is equal to x plus 2. And its y-coordinate is equal to negative 2x plus 1 because it's on this line. So equal negative 2x plus 1. Now we solve this, we add 2x to both sides, so we get 3x plus 2 is equal to 1. We subtract 2 from both sides. 3x is equal to negative 1. X is equal to negative 1/3. We are pretty happy with that because it's really very consistent with the drawing we have. Our conclusion is that the equation absolute value of x plus 2 equal to minus x plus 1 is exactly one solution, which is the one we just found. As we said in our strategy slide, there's another way of solving this equation. It's getting rid of the absolute value by splitting cases. And indeed, let me remind you what the idea was. When x plus 2 is greater than or equal to 0, then we know that the absolute value of x plus 2 will be x plus 2. And if you subtract 2 from both sides, this really is the same as that, right? So in that case, our equation, which is absolute value of x plus 2 is equal to negative 2x plus 1, since now we have the absolute value of a non-negative number, its absolute value is the number itself, and we get x plus 2 equal to negative 2x plus 1. Oh, that's the one we've just solved. So we've just solved this one, and we get this result. Let's go for the other one. So if we look at the other one, so basically we're looking at the other possibility. Either x plus 2 is greater than or equal to 0, or it's less than 0, so two possibilities. And we've split these cases because if we know that x plus 2 is negative, then we know that the absolute value of x plus 2 will be obtained by putting a negative number in front of x plus 2. So the equation says this is equal to negative 2x plus 1. Same thing here. We now distribute the negative 1. It's like multiplying a parenthesis by negative 1. So we're going to get minus x minus 2 is equal to negative 2x plus 1. So if we add 2x to both sides, and some of you are starting to worry, they're right, we're going to get x minus 2 is equal to 1, so x is equal to 3. And look at what happened here. That's the solution we had. How come we get a second one? Something must be wrong, so it's either this one or the other one. If we go back, there clearly is only one port of intersection, so nothing seems to be wrong on this side. What's wrong is actually on this page. You have to be very careful when you use this method. The calculations we've done in these columns are valid only if x is greater than or equal to 2. So here we've skipped one step, which is absolutely necessary. You need to check that the value you got is indeed in the correct range. And in that case, that would be your 0, that would be your negative 2. Your calculation is valid when you're on this side. And negative 1/3 is indeed in the correct range, so it is a solution. Let's do the same thing for the other side. The calculations we have are valid only for numbers which are less than negative 2. So they're valid only for those numbers. And look at the value we found. 3 is here. So 3 is not in the range for which the calculations are valid. Therefore, it's not a solution. So don't remember, whenever you use this method, that you actually check that the value you get in the end is in the range for which the calculation is valid. So we almost got a heart attack here, but finally there's only one solution, everything's good. Still, you probably wonder, where does the second solution come from? Let's go back to the previous slide. What you can see here is the second solution we got corresponds to the point of intersection of this line and that one. And indeed, they intersect when x is negative 3. When x is 3, sorry. So the calculations we had, we said, well, let's replace the absolute value by this line, except it's only valid when x is less than 2, and here we would get 3. This is where the 3 comes from, this solution which we had to eliminate. So now we are doubly reassured. We know where the 3 actually came from, and we know why we should eliminate it. The previous example was a fairly difficult equation. Now we want to try inequation, things like that, where you get a less than or equal to or a greater than, and we mix this with absolute value. Before we solve the two examples below, we'd like to do two easy examples that are going to give us basically the idea behind the solution. So the first one, draw on the number line the solutions of absolute value of u is less than 6. If you just try to think of which numbers would have an absolute value less than 6, I think it's pretty clear to everybody that all these numbers will work because they're equal to their absolute value, but others will work. If you try -2, its absolute value is 2. So also all the numbers on this side will work, and you can do this just by using the definition. If you think of the absolute value as what removes the sign, then basically, if you take any number between -6 and 6 and remove the sign, you will get something there. You can also see this by interpreting the absolute value as the distance between you and the origin. If these are the numbers which are less than 6 units away from the origin. Second one. We want to find all the numbers for which the absolute value is greater than or equal to 3. So clearly, if your number is 3, 4 or more, the absolute value, which will be the number itself, will be greater than or equal to 3. But again, other numbers work. If you try -4, -5, -6, -3.5, they will also work. So all these numbers which are less than -3 or equal to -3 will be solutions. Now, try to solve the following two examples. I'll give you a hint. Just try to use what we just mentioned. Let's solve this first example. So we have a number inside an absolute value, and we want to be able to tell when the absolute value is less than or equal to 4. It's exactly the same as this. If we'd like, we can even introduce some new notation and rewrite our equation absolute value of u is less than or equal to 4. And we know exactly when this happens. This happens if and only if my number is between -4 and 4, both included. Now my u really was x plus 1. That means x plus 1 is between -4 and 4, both included. And what I want is x, not x plus 1. So I will subtract 1 everywhere. So I get a -5 here. I get an x in the middle. That's what I wanted. And I get a 3 here. This solves our inequation. You do not really have to use the change of variable. If you'd like, you can go directly to this line if that's obvious for you, that if the absolute value of a number is less than or equal to 4, then the number must be between -4 and 4, both included. Let's now turn to the second example. So, the absolute value of some number, the number being x minus 4, is greater than 3. This can happen in two ways. So we can use the same idea. We could either use a new variable and define u as the number which is inside. Maybe for most people it makes it clearer that we're interested in finding a number whose absolute value is greater than 3, which can happen in exactly two ways. Either your number is 3 or more, or your number is -3 or less. So you write exactly this. Absolute value of x minus 2 is greater than 3 means that either your x minus 2 is less than -3 or x minus 2 is greater than 3. And again, you can solve by adding 2 to both sides, and you get that x is less than -1. And on this side, same thing. You want to get rid of this minus 2, so you add 2. And you're going to get x is greater than 5. So you can either draw a solution where you would have your -1, your 5, and represent so x is greater than 5, 5 not included, so it would be that. Or you could also write it using interval notation. So there are two ways of writing your solution. All the numbers between -infinity and -1, not including -1, and all the numbers which are above 5. Now this is just a recap of what we've done. Whenever we had some inequations like that, what we wanted to do is to get rid of the absolute value sign. We've done this using different methods. It could be algebra, it could be geometric. And once you got rid of the absolute value, you make x the subject. In particular, we've been using things like that. If the absolute value of a number is less than r, then the number must be between negative r and r. And if the absolute value of a number is greater than r, then either your number is less than negative r, or it's greater than. If this is more convincing to you, you can illustrate using a diagram. So for these two numbers, and that's where your 0 would be, these are your values, whereas if the absolute value is greater than r, it could be either that x is greater than r, or that x is less than r. You have to be careful when you manipulate some inequalities. Basically, you can add anything you like to both sides, you can multiply and divide both sides by something positive. But if you multiply or divide by something negative, then you must reverse the inequality. With that, you have all the tools you need to solve inequations containing absolute values. Let's try a hard example. So, we want to solve this inequation. If you look at it, it says that the absolute value of some number is between 2 and 7. So instead of trying to find x directly, let's try to find which numbers have an absolute value between 2 and 7. So we could give a name to what's inside the absolute value. Let's say we call it u. And then the inequation, which I'm going to call star, becomes absolute value of my number u is between 2 and 7. And you could use a number line to try to visualize. So I'm sure a 2 will play a role, so will the 7, but the negative 2 and negative 7 will be important too. If the absolute value is between 2 and 7, either my number is itself between 2 and 7, but if you think of the absolute value as just removing the sign, if you have any number between negative 2 and negative 7, sorry, that's an open circle, for those also, you will have an absolute value between 2 and 7. So what we said here is that the solution of the inequation corresponds to either u is greater than, either u is between 2 and 7, or u is between negative 7 and negative 2. Note that if you have the drawing in front of you, I'm pretty sure that you will put the negative 7 and the negative 2 in the right order. Now u, we said, was defined to be 2x minus. So we can add 3 everywhere. So if you add 3 everywhere, this becomes 5, this becomes 10, and here you only have 2x left. Now we want 1x, not 2x, so we divide everything by 2. This becomes 5 on 2, this becomes x, that was the goal, and this becomes 5. Now let's solve the other one. Again, u is equal to 2x minus 3, that's how it was defined. And we're going to be using the exact same thing. We first get rid of the negative 3 by adding 3 everywhere. So we're going to get a negative 4, 2x, and a 1. Now we have 2x and we want 1x, same thing, we divide everything by 2. And we get that x is between negative 2 and a half. And again, we can represent the solution on a number line. That's our 0. That would be, so that if this is 1, that would be a half. I need a half. I need negative 2. I also need 5. 2, 3, 4, 5. And I need 5 on 2, which is basically 2.5. So it's going to be there. 2.5. Now let's represent the solution. All the numbers between 5 on 2 and 5. So all these numbers are solution. And also all the numbers between negative 2 and a half. So that can be a way to represent the solutions. And of course, an alternative way is to use interval notation. So that would be all the numbers between negative 2 and a half, and all the numbers between 2.5 and 5. Let's wrap up what we've done here. We discovered a new way to think about the absolute value. That is, when we see the absolute value of x minus c, we know that this can also be thought of as the distance between x and c. This, together with the methods we already had, has given us 4 ways to solve equations containing absolute value. Sometimes just use the definition. If you know that the absolute value of a number is 3, well, there are only 2 numbers. Sometimes we've been splitting the domain, as we said, considering the absolute value as a distance or sketching a graph. We then have pushed it a step further and learned to solve inequations involving absolute values. Thank you for listening to this video.